So yeah, hi everyone. Welcome to the next talk in our series 2 of the EDT community talks. It's good to see you here. Today we have a great talk lined up, but first I'm just going to do a very brief overview of the kind of upcoming talks and the schedule for the next few weeks. So we'll be continuing with our usual schedule of one talk every other week, ending with another panel discussion on the 7th of March. If you didn't attend our panel discussion from series 1, you definitely missed out. We had some great conversations, so we hope to see you here this time around. But without further ado, I'd like to introduce Peter Gorm Larsen from Aarhus University, who's going to give us a talk on the possibilities with digital models, digital shadows, and digital twins for cyber-physical systems. Peter Gorm Larsen is the Deputy Head of Sector and Professor at the Department of Electrical and Computer Engineering at Aarhus University. And on top of that, he also leads the Cyber-Physical Systems Research Group, as well as the Centre for Digitalization, Big Data and Data Analytics, and the AU Centre for Digital Twins. So we're very excited to have you here, and I'll hand over to you.
Thanks very much. I'll try to share my screen. So I hope you can see that now.
Yep, we can see. Very
good. So thanks very much for the invitation to speak for this audience. We have already talked, the title have already been mentioned, and as you can see on the small figure here, digital twins is way high on the hype curve from the Gartner Group. And as you can also see, I have a few different hats to wear, which also mentioned as well. So I would like to start off by giving you an overview of the digital twin projects that we actually have in the section. And these are virtually all related to digital twins in one way or another. The ones that have are named in boldface are projects where I am the PI, but I'm also involved in a few others where I'm not leading it, but others are leading it. What's worthwhile understanding here is that we have quite a lot of funding from these different projects. The numbers here given in Danish kroner, or million Danish kroner. If you divide it by 7.5, you get the same things in euros. So it's more than 100 million euros in total for the projects, and more than 10 million euros for our part alone. Now I'll come back to some of these projects later on, because they vary from, say, very generic kind of digital twin projects to very specific on manufacturing, agriculture, vehicles, building, and different kinds of areas like this. But this, of course, also means that there's a rather large group of people. These are the people in the section that are related to research and innovation projects. There are permanent researchers, there are postdocs, and there's currently 10 PhD students, and there are 3 more that are being recruited. And then we have some people who are part-time involved in the research and innovation activities we have here at the department, all in the section that I'm leading. Now, there are 4 different kinds of things that I would like to talk to you about today. I'd like to start off with making sure we all understand what cyber-physical systems are. And then I would like to kind of give a small introduction to some of the kinds of tools we have been building for model-based analysis of such systems. And then I'll go into the digital models, the digital shadows, and digital twins, and finally end up with the kind of tool support we have gathered, all belonging to a non-for-profit association called the INTO-CPS association, and the tool chains that are in that, and also kind of get you a glimpse of what the kind of things we are able to do. And essentially, you can say that the IP of the different projects we are involved with, it goes into this association such that it actually becomes have more and more IP and more value for those who wish to build models and digital twins in general. But let's start with cyber physical systems. I would assume that most of you know that cyber physical systems are systems that have interaction between computing elements as well as physical elements, possibly also with human interactions. They typically have a complex network architecture and also can have distributed control. And therefore, because they are quite critical, it's important to be able to detect errors and try to recover from these. You see the pictures you see here are from some of the different projects we have been involved with over the years. And these are demo cases that can be used for demonstration of the capabilities we have developed. In general, I like to show kind of a schematic thing like this. The blue plant thing is the physical thing. The physical thing typically, let's say, described properly by mechanical engineers. The yellow part there is typically the controller, the thing that kind of takes things from sensors on the plant and send things to actuators on the plant. And in most cases, you would only think of the controller on the plant, that's the cyber physical system. However, the cyber physical system may in some sense also be dependent upon the environment in which it's residing. So for example, if we have an agricultural vehicle driving on a field, it depends very much on the kind of surface that it's driving on. And if it's been raining for a month, the performance will be different from the fact if it's been dry for a month, for example. Now, we have had a series of EU research projects. The ones I showed you before, the ongoing projects, and they were funded both by national funds and also by international things such as Horizon Europe or Horizon 2020. Now, the current things are getting into applications into Horizon Europe. But if we take those projects here, they have the DESTEX project, which happened a long time ago, resulted in a book. I have it on my shelf over here in order to try to say, okay, how can we actually build embedded control software and how can we take the physics into account? We also had a project called Compass related to system of systems. Here we also produced a tool not used as much as the tool that came afterward. The INTO-CPS project, which I was the coordinator of, was an 8 million euro project where we had this open tool chain coming out of it. And that the IP from that project is now owned by a non-for-profit association. And we actually continue to throw more stuff into that, which I'll come back to later. Now, at the moment, I'm also coordinating another project called HubCat, which essentially tries to do model-based design directly from a browser and have an ecosystem around that. So if any of you are from small and medium enterprises, you should take a look at the web pages for that in order to see if there's anything for you to actually gain from, in the sense that we are giving out 3 million euros to SMEs and involvement in this platform. I hope that by this you have a good feeling for what cyber physical systems are. Now I'd like to show you some of the tools that we have been able to produce to make model-based analysis of such cyber physical systems. And a lot of it is based around co-simulation. The paper that I'm citing here is from the ACM Computing Survey. And this is kind of giving a survey of different techniques for being able to combine simulators together. And when you have a cyber physical systems, it's characterized by having control, typically based on discrete math, kind of mechanical thing or electronical thing, typically based on differential equations. These different kinds of mathematics are not necessarily and very seldomly present in one tool. And therefore, what we are working a lot with is how can we combine different simulation things and couple them together. And that's what we are following, mostly a standard called functional mockup interface coming from the automobile industry. Now, the INTO-CPS tool chain went all the way from requirements, also using SysML, some of you may know, and being able to automatically generate the skeletons for the models that can be used in this FMI context, and then having heterogeneous models that you can do typically co-simulation model in the loop before you kind of go over to a production of either real code or real mechanical hardware. And then we had tool support that kind of enables strong traceability based on something called OSLC, and then being able to do configuration management, do design space exploration, and test automation. I'll show some glimpse of some of these things, and I'll twist it up to digital twins later on. Now, if I continue, I'll try to show you a small example of how you can do a design space exploration. This is an academic case study where you have a small robot moving along a line, typically child kind of thing. But what you see here is a number of videos put on top of each other, and each of them have are chosen from a Pareto front of the optimized ones, given the placement of the sensors. You see the orange one is very slow, but it follows the line very precisely. Some of the others are more like Formula One cars driving too fast and getting ahead of the pack. But the point here is that this is an excellent way of being able to visualize for, in particular, non-technical people, what's the consequence of different design choices, so you can make a decision on what are the things you would like to go for. Now, to give you a more industrial case, here you see an autonomous robot used in agriculture. It's from a company called AgroIntelli. The first versions of this robot was produced in the INTO-CPS project. It's now a commercial product. It weighs 1.5 tons plus the instruments you have on it. And you can see this one, for example, is stopping to spread poison on the field after it's done what it needs to do. And essentially, this kind of doing dynamic models of cyber-physical systems and their control is what made this product go as far as it did. They got an investment for around 20 million euros last year, and they are flying away and selling these all over the world now. In general, with respect to modeling, I think that the thing that's changing now and really going to have a dramatic difference for time to market is that instead of having a series of prototypes, you still need prototypes, but maybe not as many as you did in the past, and having document-based things where, in particular, testing of the physical context can be expensive. Maybe you can't test all year round. What's happening now is that digitalization is creating disruption. You're combining models for cyber parts, for physical parts, and then we can include game engines to visualize things, which makes it cheaper, much cheaper, and it's possible to feel a product before it actually exists. So to give an example of that, I'll show you a device that's going to help getting people to offshore wind turbines. What you see here is a ship. On top of this ship, we have this crane, but the crane here is compensating for the waves of the ship. If you look carefully, you'll see that it's moving up and down, except the front of it is standing entirely still. I have an ability to show you this in Oculus Rift glasses, where you can experience like what's it like controlling this and moving over to the actual platform with or without the control, with different kinds of wave severity. And you can see the main difference. You can feel the difference even without having the product. That, I think, is going to make a major difference from a time to market perspective. So that's one thing that we can use digital models for. Now I'd like to go into the distinction between digital models, digital shadows, and digital twins. And what you've seen in the past here essentially are a digital model and then the corresponding physical model. Let me try to put a pointer on here. So you can see the legend down here is saying that the dotted lines are indicating there's a manual flow. So a human is kind of comparing what's happening in the digital world compared to what's happening in the physical world. Now, if you think 3D printer, essentially a 3D printer is something that kind of have a digital object and in 3D, and it can print either in metal or in plastic or whatever, a physical object. So it's automatically going from the digital layer to the physical layer. Now, digital shadow is going the other way. Here we have a digital object. We have some sensors on it that are able to real-time stream data to a digital object, which can be fed with this, and possibly visualizing things like I've shown for the line following robots earlier on. But, oops, I want to go this way. Digital twins essentially have an ability to automate the flow in both directions. That is the, I wouldn't call it the holy grail, but that's the target that some people are opting for. But there's a lot of considerations to make before going there, because when do you want to remove the human from the loop? There are dangers, in particular, with respect to safety and security with respect to that. Now, we have some small case studies. One of them, the most simple one, is called an incubator case study. So what you see over here is aluminium, fuel kind of box that is isolated. And then inside it, there's a heating device that can become very, very hot. You don't want to touch it, trust me. There's a small fan, and then there are some sensors that can sense the temperature at different places. And then we can have a model like this model over here, which is kind of like a continuous flow dynamics model, which can change over time how the temperature changes depending upon the heat of the plate being controlled from a controller outside. And such a model can be very, very slow in simulation, but we can make approximations of that using reduced order models, so it can run in real time. Well, what's more important is that we're actually able to detect faults when they're happening. So if, for example, I take the lid off this thing, obviously, then it becomes the volume that it needs to heat up is much larger. And therefore, it'll take longer time, but I can detect that the constants have changed. I can use Kalman filters to get back on track in order to kind of say, well, where are we now? Where we're supposed to be now, so I can follow even the new situation where faulty situations are actually present. So the way we are doing this is that we have a physical twin. You see it over here with a small Raspberry Pi component here at screen and connections to that. And then we are feeding it over to the digital shadow by means of a RabbitMQ, so MQTT kind of server that can enable us inside the digital shadow both to record the data, put it in a database, but also to do feeding of the models runtime by means of an orchestrator that can then enable you to do what-if analysis. What happens when if I would try to do this to the model, if I open this lid, if I did this other thing, and then do state estimation in general. But if I wanted to do a digital twin, I needed to have also a kind of a configurator over here. So I would be able to say under what circumstances would I like to transfer knowledge over some communication layer to a configurator that's local to the physical twin. I'll show you an example of that on what's called a desktop ROBOTTI version, which is less dangerous than if it's a 1.5 ton kind of device. So in general, what's interesting for the research we are doing is how can we engineer such digital twins? So over here, we have a digital twin version of the plant, digital twin version of the controller, and we have some kind of approximation of what we expect the environment in which they behave to be. Over here, on the right-hand side, we have the physical version, the physical twin version of the plant, the physical twin version of the controller, and of course they have interaction, but they have interaction to the real environment. So each of these boxes can be seen as a function of the input and the state to its output. And of course, we need first and foremost to align the initial states so we know where are we. So we need certain calibration things to happen in respect to that. And then in addition to these calibrations, we have to realize that because we have discrete readings of the physical signals, and that it means that there's always going to be a discrepancy between the performance in the physical world compared to the virtual world. But we need to kind of keep it in mind that we have alignment of these. And we need to kind of say, we need to consider what the safety concerns we could have for how it could affect the environment. Like if there were people in the environment or animals or other things that could be damaged by it. But also you could imagine that there could be threats in the environment. People who want to take over your control of your autonomously driving car, which have been reported numerous times already. So we also have more realistic kind of case studies, more industrial-like. What you see here is the universal robot, 6 layers of configuration. And then we have also a digital twin version of that, where we can try to play out with different things based on the model we have of it. Now, what we try to do here is we try to predict the current at each joint in addition to its position. And we have a maximum, in this case, a 5 kilo payload. And here we want, in the future research, to be able to automatically detect what's the weight of the payload that's placed at the endpoint device out here. Of course, in order to have a model of this, you require some mathematics, physics. I'm not going to go into this, but this is essentially the equations that are based on each of the joints that we have in here, depending upon the gravity, and then you have yet another coordinate system at the next layer, and that needs to be taken into account. But what we try to do here is we try to have parameter estimation. So estimation is done at one level, and then when you have estimated the parameters, you need to validate the parameters actually fit the real system. So Universal Robots as a company, they have a tool called UR interface that you can install like this, and it works perfectly for these things, except they don't have the system identification and the estimation thing. We have built that in another tool. One of these tools belonging to the INTO-CPS association is called AU-RT, the robotics tool, robotics technology tool, which can be installed in exactly the same way. And this enables us to kind of runtime get data from the robot as a stream of data. So if we try to gather such data, so you see here, I'm making the robot doing different kinds of moves. What you see down below is the position, the angle for each of these 6 layers. And then at the bottom layer, you're seeing the current that's for the motors at each of these layers. So here we record it now, and that's recorded using the AURT thing. Now, when we then have this recorded, we can actually calibrate it. So just like I talked about before, we have a calibration phase and a validation phase. What you see as the dotted lines that are kind of on top of the other ones here, that's actually the calibration things. But when we then have completed this, we can automatically export this to an FMU, a functional mock-up unit. as an independent unit that can be coupled together with other things. So we can do simulations with that on its own. And we can also, as a digital shadow kind of thing, visualize it. So what you see here to the right top is actually a visualization made inside Unity. It's a game engine, which is trying to show how are things moving. And it's purely based on the position information that's here. So that's a digital shadow kind of thing. And in order to kind of easily integrate this into an FMU, we are using another tool that I'll come back to later. So I'd like to say that in the research group here, we're doing the full circle. We go from basic research over innovation and then to education. So I received some funding. That's the first project you saw up there from the foundation that owns a company called Grundfos. Grundfos is the largest manufacturer of pumps in the world. And they give out funding to different things that are of good nature. Here is independent research to kind of say what's the limit of digital twins. We have a series of projects which are more applied research together with external partners, where we also look into combinations of first principle models with machine learned models, visualization as you've just seen, but also scaling up to system of systems level. We also try to do digital twin innovation, typically together with small and medium enterprises. In Denmark, we also have a kind of organization called Global Technology Services. They're like Fraunhofer in Germany, and they are helping in particular SMEs, and we typically collaborate with them in order to kind of get the technology transfer working in the best possible way. We also act as a digital innovation hub, which gives advice to people about how to get started with digital twins, when it's worthwhile doing it. But we try to take our research results and test them on our educations, which means that new student research projects are using these research results and then generating new results in general. So now at the end here, I would like to go into show you a little bit about what we have done in this INTO-CPS association and what kind of tools we have at our disposal in here, and how we actually, when we have new results from these projects, we push the technology into this tool chain. So essentially, you can see there are 5 areas in which we have things. We have things in relation to co-simulation. Our first tool was called Maestro. We have a faster and more flexible version of that called Maestro V2. We have a graphical front end on top of that, and we have a way of, let's say, verifying that scenarios you put together actually will work and be semantically true to what the real system will do. We have design space exploration. I actually showed you the output of one of those, so I'll not kind of go into the different techniques that are there. But then we have a number of tools for, let's say, making it easier to get plugged into this FMI standard support. Currently, version 3.0 of the standard is being formulated, and we are also involved in the standardization group for that. But the kind of tools include this AURT tool I showed you a little bit of, and then something called UniFMU, which essentially enables you from any programming language to couple it into becoming an FMU. An FMU needs to have its interface in C, but we can actually generate that C from this tool. And then there's something for checking them. It's made in a notation called VDM, which I have been doing a lot of my research in the past, but it's a precise formal notation to be able to describe the conditions under which an FMU is correct and live up to the standard. And then we have RapidMQ, which is an MQTT bridge between a physical twin and a digital twin. We also have capabilities in terms of system monitoring. You've seen already this Unity FMU example where you can do 3D visualizations. You can also couple that to other kind of glasses like Oculus Rift glasses. But But then we also have Kalman filtering to kind of get back on track. We have visualization in kind of like 2D dimensions in terms of how curves are like a dashboard, how it's evolving. But finally, we have also very recently been developing fault injection capabilities in order to be able to explore potential failures at an early stage, and also be able to use that for training purposes for a real system that is deployed. So now I'll show with a few slides some of these different things, and I'll start with the co-simulation thing. So if we have a control part, we have a plant body thing, and we have an environment, then we would typically develop these different models by means of different tools. And essentially they have set and get operations and then taking steps in time. So different tools would typically be used for different things. And it's the beauty of this is the interoperability. So it actually hangs together. What I've shown over here is some performance curves in a paper that has been submitted, but is not yet published, which compares Maestro, the original Maestro we made in terms of performance, and then our Maestro 2. And finally, a code generation version of the Maestro 2. So both of these are actually interpreted, but this last one have been generated to plain C code. And you see it's quite a lot faster, both without loading the FMUs for real and also with loading the FMUs. So gives you some kind of performance indications. The structure of this newest version here is a matter of trying to have a configuration which is being used to generate a specification written in what we call Maestro-based language. It's a domain-specific language which then is being parsed, is being type-checked and expanded upon, and then it's being verified that, yes, this will actually work before the interpreter is called or the generated code is being used. So this is essentially the basic structure of the Maestro version 2 thing here. Now, UniFMU at the moment has been instantiated with Python and C#, but also with other environments like Docker and Unity. And essentially, it's a matter of trying to get C code generated so it's easy to connect any piece of code you wish to do for part of your system to C, and then the standard for that. That's also being used for the Unity integration. Unity is coded in C#. You've already seen me simulating parts of this with the UR robot thing. Here's this picture from the incubator. And of course, we have more of those. Now, the connection between what you see over here, the INTO-CPS application, that's a graphical front end that can have different what's called model descriptions, which each are exported to be FMUs, can then be orchestrated either using Maestro or Maestro version 2, and then we get some results. And the connection of this to a real world, either a real physical robot like this, here data is stored in the AWS server in cloud, but it could also be Gazebo. It's another simulator where you simulate things, you see how it would work. And then we connect the data here using this RapidMQ thing. The more later thing that hasn't been published much yet is about if you have these different connections for FMUs, you can actually try to do fault injection. So it would kind of say, well, I'm going to inject this fault here, particular place at a particular point of time in order to see how does the rest of the system behave. This can also be made in terms of like a file for events that's going to happen. And then there's like a wrapper being produced around an FMU, which kind of can send data through standard without any kind of intervenience, or it can intervene and say, okay, I'm going to do something with this particular stream of data. And that can be the fault that we want to see and how to analyze how it can impact the rest of the system performance. So here's the very end. I'll show you a small video. What you see up here is a desktop version of the ROBOTTI. It's like 70 centimeters and not several meters, and it's 5 kilos rather than 1.5 tons. Here, the cross, the intention is there's an obstacle. And over here, you see the 2D visualization inside the INTO-CPS app. And here you see, let's say, a grammatic thing of where this one is placed, where the arrow is placed. And down here, you see the communication. So in a sense, what we're trying to demonstrate here is how data is sent from a physical twin up to a digital twin. And then the digital twin is going to send a stop signal before we reach this obstacle over here in good time. So let me try to start the video. And you'll see this is how the runtime thing is shown in the graphical thing when performance is done. You see the robot is driving over here, and now it's getting to the area where we would like it to stop. And you see the signal here, and therefore we'll stop and send a stop signal down to the robot over there. So the very last slide I have is with a few links. I assume that I'll send you the slides afterwards so you can take a look. But there are some home pages for this INTO-CPS association, which may be worthwhile for you to inspect. In case you wish to become a member, just send me an email. You can either be a member by a paying member, or you can pay in kind. We also gave a tutorial October last year about digital twin engineering, about using some of these things. You can find the videos for that here. In case you want to play with the incubator, we have an emulator of it. So in case you want to try to use your own pet formalism to try to make a digital twin using this example, that would be easy. This incubator, all the material of that is in a technical report, so you can buy it and it'll cost you like 100 euros in total. The RapidMQ thing, which is being developed, is here. The fault injection plugin is down here as well. So now, in case you have any questions, I'll be ready to answer.
Great, thank you very much. That's a great talk and really insightful. So yeah, I'll hand over to any questions we have. I have noticed one in the chat from Andreas Wortman. I don't know if you want to ask that in person, Andreas?
Sure, thank you very much. I should show camera maybe. Hi, so first of all, thank you for your talk. I like your perspective very much. I'm wondering, so you had this slide, I think it was 22, with digital shadow on it. Yeah. In there, it looked like a digital shadow would comprise simulators, or at least simulations or simulation models. I'm not quite sure about that. And now I'm wondering, can you try to characterize, maybe a bit more precise, what a digital shadow is for you and what it does comprise?
Well, I think to me, the main difference between a digital shadow and digital twin is that a digital shadow is flowing, the information is flowing one way. Whether you use that flow of data in a visualization doesn't matter. That could be one way of doing it. But the point here is that you are not automating any kind of transition down to the digital twin in a digital shadow. You may have, let's say, another way in which the human being watching the data and watching the progression of things in a digital shadow is able to do things with it, but it's not automated inside the same connection, so to speak. So the digital twin, in my view, is the ultimate goal where you actually have the possibility of automating it, even without a human in the loop, which can be dangerous. Therefore, it needs to be done with caution. And that's where I'm advocating that you need to use proper system engineering techniques. And we are currently also writing a book on digital twin engineering, where these are some of the advanced features that will be touched upon in there. Did that answer your question?
It did, thank you.
Welcome.
Great, thank you. Are there any more questions from anyone else?
Don't be shy, I'm not biting.
Yeah, I'm not seeing any hands. Oh, there we go. Question from Mark.
Yes, also thank you for the nice talk. In reaction to what you were just saying, the involvement of the human being, to what extent do you also then take, let's say, certain standards into consideration for instance, functional safety, to ensure that indeed the people involved in the equipment are not being jeopardized?
Yes, so I mean, this is a very good question. There's no doubt that in case you want to get a safety critical system certified, you need to take this into account. And that's exactly the reason why we are trying to see what we can do to improve what I would call the current, maybe naive expectation by some of the commercial suppliers that kind of say anything is possible. I think that it's very important to kind of go away from, let's say, the kind of banana culture we have, for example, for drones, where people are just trying things and maybe it works, maybe it doesn't work. I think it's important, if we are serious about doing digital twins, we need to make sure that digital twins add to the dependability of the system rather than make it worse, in a sense. Did I answer your question?
Yeah. And I fully agree to what you're saying. And I'm wondering to what extent then indeed the digital twin can be helpful there. So I can imagine that you can do all kinds of bad weather behavior or scenario thinking, where you say, suppose that this happens. So you show this example with the robot that stops at a certain point, but especially, let's say, if you have such a robot that does the spraying of a field, that if it detects, for instance, a animal or so, that it indeed also goes into an emergency stop in order to not to hit the animal if the animal has not gone by that time.
Clear. And actually the robot there do have such an emergency stop. But the intention is that it should be operated autonomously, so without necessarily a human being right next to it.
Yeah.
So maybe a human sitting on the other side of the earth. And therefore you need some connectivity guarantees. For example, then you look into, well, if we haven't had any kind of like a dead man switch for trains, if we haven't had any reaction in a certain amount of time, maybe we need to stop going until we actually get connection again. These are the kind of safety cases that needs to be made. And I think I would strongly advocate for doing that instead of just, let's say, naively thinking that anything will go. So there's a question from Stefan. The question about your example, Mark, where the controller stop and the digital twin start. And the way I'm looking at that is that you have a controller that's a part of a cyber-physical system. And I'm looking at the things that the control that is residing in a digital twin as more supervisory control. So not with very let's say, low latency things, because then it would not fit for doing things. The things we are looking at for the fleet project for these ROBOTTIs is to be able to actually reroute some of them in case one of them have to stop. There's something is wrong with one of them. But the control would in my mind, be more supervisory of nature. And there's of course a gray line in terms of where do you place things. But to me, the digital twin is essentially needs to give you more information. You need to be able to answer questions based on that to human beings. And if you trust it, you can do it and kind of close the loop and do it directly. And I wouldn't do that every time.
So can I just follow up on that perhaps briefly? I think there's two things that were interesting in what you've just said about that. One is that it's the digital twin that you use for controlling, sort of a fleet of robots, for example, which I think asks the question of what level of detail do you actually then need in that digital twin, right? Because you showed us the digital twin of these ROBOTTI robots that actually had a sort of a geometric replicate of the digital twin, which presumably you don't necessarily need if actually the question you want to ask is about rerouting a fleet of robots. There you might go with a much more abstracted view of the robots that just looks at positions. But the thing that perhaps is slightly even more interesting for me was that distinction of saying the controller is for sort of autonomous behavior of the system, and the digital twin is for showing relevant properties of the system to the human for human decision making. Would that be sort of a distinction that you would support, or did I misunderstand what you said?
Well, no, I would agree in terms of initially that's the way you would look at it. In case you after some time, let's say you have a human in the loop, and in 100% of cases for X number of years, you have now seen a human doing exactly the same thing. Then you may take the leap and say, well, okay, let's automate that part. And of course, it depends on what's the risk involved in doing so. But I think I'm seeing it as let's say, a gradual transition where the digital twin has more capabilities than it's going to explore initially. And then you would gradually kind of say, well, now I trust it enough. I'll check that extra feature in a sense. So it's like if you have a car and it has more features than you can actually use initially, but you don't need to give the person a new car. You can just say, now I trust that more. With respect to animals and being able to hit them, animals are being hit by these kind of machines. Also human-operated things, because let's say a small deer would kind of duck down and try to get away from a harvester, for example, and it's very bloody and it's not pleasant. But then what we have been looking into are how can you actually have ultra red cameras that can see the heat map of these things, so you can stop before it. And these are kind of things you can experiment with. Well, what's the cost of trying to put on additional sensor, and what's the gain you can have from it? If it kind of prevents you from stopping for a long time, or the thing you are damaging is, let's say, troublesome for the people around it in the environment, then you may do this, say cost benefit analysis in a sense. But to me, it's a matter of trying to enable the technology and then gradually deciding upon when you want to instigate it, so to speak.
Yeah, it's very interesting. Do we have any other questions from anyone else? No, it looks like that's it. So yeah, thank you very much, Peter, for giving your talk. It was very, very interesting. And I hope everyone else enjoyed it too. Yeah, I see some artificial clapping there. Okay, thank you very much, everyone. And I hope to see you in 2 weeks' time.
Thank you. Have a nice day. Bye.
Have a nice day. Bye.
Goodbye.